So what is the output of, say, the first one in any particular scenario? So let's say we have psi implies, sorry, phi implies psi. In the truth table we have x and y, so let's just use basic substitution and just replace those. Just in your brain, think of these as x and y for for just to explore the underlying notion, okay? So let's say that we have. I'll make it easier actually. No, never mind. That's too much work. Anyways, moving on. Okay, so the first one. Phi involves psi. Phi implies psi. So phi implies psi, x implies y. Let's look at the first scenario, 1. And we're gonna try and start from this combination, which is this expression, and build the following expression, if it is possible, to match every single value after building it for each of those scenarios, like this scenario, this scenario, and this scenario. Then this is an absolute equivalence, because the total combinations that both can hold would be the combinations that exist in the number of variables that we have, which is 4 combinations. So let's see. And the more variables you have, it's just a power of 2. So the number of combinations that you have. So this is 2 squared. You got 4. If you had only one variable, you'd only have, like in this case over here, we have to the 1, and that's one variable, and the result is 2. So this is the number of variables. So one variable, base 2 is by default what we have when we do these sorts of operations, binary operations, so, or combinations, and the result is 2. So, and the result is that we have 2 rows, 2 combinations possible. Okay. Let's move on. Okay. So then we were here, yeah. So we're gonna try to arrive at this particular expression from this expression. So what we have is x implies y. We have the value that this expression returns, which is 1. If we go to the base values, which is x and y, sorry, the variables, the values of the variables of x and y, and we do what occurs in the transformation, which is first off the negation of phi, or the first variable. So we negate the first variable. It means that this 0 will become 1. And what we do after that is we search a match for that, and we find it down here. The one that should go here is down there, right? And if we go back to the expression, we can see that it's different, right, from the original. This and this, they're different. And why? Because we've transformed it. We've added a negation to it, and we haven't yet changed the operator that becomes the disjunction. So let's now think of doing that. So to do that, so we've arrived at this by negating x, but now we want to perform the disjunction after performing the negation. So we remain on this row, but we go to the disjunction column, and we see that we have a result of x disjunction y, which is 1. And if we compare the results that we have in the first one and the results that we get in the disjunction after the negation, we'll see that it's the same exact result. In a similar way, we can explore, and we should explore all of the other scenarios. This is because there are false positives, right? As you'll see in a second. So let's see the second scenario. We'll nullify x and go back here, right? And so x will become 1, and we'll see the matching pair, which is down here, 1 and 1, and we'll go back and see that the result is 1. But we know that we still have to substitute the disjunction operator. So we go to this column, maintaining the same row, and we can see that the pairs match. Tracing back to the method, let's look at the second result, and we negate x, which is phi, and we obtain 0, so 0, 0, which prompts us to look to the first matching pair. And the first scenario, when apply the disjunction, we'll look at here, right? First off, what I mentioned earlier is that, so actually, never mind, let's keep going. So what we obtain is 1, which is different from what we obtain in the initial condition. And then we'll look back, and here we go. There's a 0, and these are equal. So we apply the same exact method for the last one. We look here, we negate the first one, leads us to this conclusion. We follow the row back to the expression, and we replace it by the disjunction, and we notice right over here that they're the same. We have to follow this process. It's undoubtedly long, but it is simple after practiced, after trained. Doesn't require, it's mostly repetitive once you recall the sequence. And the sequence, it doesn't really involve that much steps. Just have to ingrain it in your logical train of thought. So good luck with that. For a total brain annihilation, let's give it another mind-twisting quote-unquote property. This one is the hardest, I'd say. Well, it's much easier after understanding the basic one, but, well, to be honest, I wouldn't even qualify it as the hardest. I'd say it's the same difficulty level. So what we're saying now is that, we have this expression. So phi mind froze for a second, implies psi, which is equivalent to the negation of psi, implying the negation of phi. How could this be, right? I was just kidding with you, this is extremely easy. Because, well, for the same reason that we say that 0, okay, whoops, the same reason that we say that if the value equals 0 on both, if we negate this, the first variable, so say that we negate phi, and we negate psi, then if psi were, for instance, if we gave it the input 1 and 0, and we obtained from the nullification of each 0 and 1, and if we say that such that if we say that 0 implies 1, okay, and this output, so the output of the implication is 1 henceforth, or therefore, well, by assigning the same values here as input for phi or psi, if we assign 1 and if we assign 0, we'll get the exact same. Basically what we just did is we swapped places. See, and by doing that, if we want to keep the implication, we have to nullify them both. And this is, in fact, this last one is a property. The middle one is more of a brain exercise, an explanation of how you can get a proof out of some of these operations. They're consequently more, to say this in more easy terms, they're more result oriented than proof oriented, like deduction formulas and stuff.